So welcome to this class. In this short video, we are going to demonstrate the concept of matrix multiplication. And remember, we are continuing with the operations on matrices. So if you haven't done the addition, subtraction, and scalar multiplication of matrices, please watch the previous video. So let's define matrix multiplication, and then we'll do some examples. So we say if Aij is an M by N matrix, and B given by Bij is an N by P matrix, then the product AB is defined and is a matrix of order M by P. So in general, the product AB, where A and B are matrices, is defined if and only if the number of rows or the number of columns of A is equal to the number of rows of B. That is when the matrix multiplication is defined. The columns of the matrix to the left must always agree to the rows of the matrix to the right. So that's why we are saying that if we have a matrix A of order M by N, the matrix B of order M N by P, then A by B is defined. So the thing is that when you observe the sizes of these matrices, so these numbers must always agree. These columns of the matrix to the left must agree with rows of matrix to the right. So that is the condition. So examples. If I have A given by -1, 3, 4, -2, 5, 0, B given by -3, +2, and then -4, and then 1. And I have, so this, say I have C given by 1, 2, 3, and 4. Then I can have these operations. AB, because these are matrix of order 3 by 2, these are of order 2 by 2, these of order 2 by 2. So AB is defined because these are 2 columns, 2 rows. So I'll have A minus 1, 3, 4, minus 2, 5, 0, multiplied by minus 3, 2, minus 4, 1. So once you have already confirmed that the number of columns of matrix to the left agrees with the number of rows of the matrix to the right, multiplication is defined, and then this is how you carry out the multiplication. It's always row by column. Because this is a 3 by 2 matrix, and this is a 2 by 2 matrix, then the columns to the left and rows to the right are agreeing. So these 2 numbers are agreeing. So you know that our resulting matrix will be having order 3 by 2, meaning that it will have 3 rows and 2 columns. So this row by this column, so I'll have -1 times -3 plus 3 times -4. That's the element in this position. And then element in this position would be -1 times 2 plus 3 times 1. And then the element here will be this row, this column. So 4 times -3 plus -2 times -4. This one here will be this row, this column. So 4 times 2 plus -2 times 1. And then lastly, the bottom here will be this row, this column. So 5 times -3 plus 0 times -4. And then this row, this column. So 5 times 2 plus 0 times 1. So then this will give me -1 times -3 is 3, -12. And then this will be -2 plus 3. This will be -12 plus 8. This will be 8 minus 2. This will be -15 plus 0. And this will be 10 plus 0. So next, then just get those sums. -10 plus 0. So 12 to 3 minus 12, I'll get -9. -2 plus 3, I get 1. This I get -4. This I get 6. This I get -15. And then this I get 10. So that's what I get. But note that if you say BA is not defined, since you see B was 2 by 2, and then A was 3 by 2. So these 2 numbers do not agree. If they do not agree, then you can't define that multiplication. So BA is not defined for this example. But you can define B, and you can also define BA, because all you can define BC and also CB because they are 2 by 2 matrices. So BC and CB are defined since these are matrices, these are square matrices, so whichever order, then you have the same columns on the left agreeing the right, rows on the right. So if I have a matrix 1, 0, 3, and then 2, -1, -2, and then I have a matrix -2, 4, 2, and then 1, 0, 0. And then I have -1, 1, -1. And then I have, say, -5, 7, -1. And then I have -3, 6, 6. Assuming I call this one C, I call this one B, I call this one A. Then the order of A is 2 by 3. This is 3 by 3. And then this is 2 by 3 still. So you see A, B is defined because this A has 3 columns, B has 3 rows. And then, so this is defined. But AC, this is 3 columns, 2 rows, not defined. And the product BC is not defined because B has 3 columns, these 2 rows. But CB, C has 3 columns, B has 3 rows. So this is defined. Good. And then if I have matrices 3, 4, and then -2, 5. If I multiply by another matrix 1, 0, 0, 1, then I get 3 by 1 plus 4 by 0, and then 3 by 0 plus 4 by 1, and then -2 by 1 plus 5 by 0, -2 by 0 plus 5 by 1. So this gives me 3 plus 0, 0 plus 4, -2 plus 0, 0 plus 5, and I get 3, 4, -2, 5. Remember, this is what we call identity matrix. And if I have 1, 2, and then 1, 1, multiplied by -1, 2, 1 minus 1, I'll have 1 times -1 plus 2 times 1, 1 by 2 plus 2 by -1, 1 by -1 plus 1 times 1, and then 1 by 2 plus 1 by -1. So this will give me -1 plus 2, 2 minus 2, and then -1 plus 1, and then 2 minus 1. And this will be -1, +1. So -2 plus 1 is +1. -1 plus 2 is +1. 0, and then 0, and then this is 1. So matrices, so if we call this one A and this one B, if they give the identity matrix, then we say A and B are inverses of each other. So where the product is giving an identity matrix, then you get, you say that those two matrices are inverses of each other. And if I have a matrix 1, -2, -3, and another one 2, negative 1, 1. This multiplication is defined because this is a 1 by 3, this is a 3 by 1. So you just get a 1 by 1 matrix. It should be 1 times 2 plus minus 2 times minus 1 plus minus 3 times 1. And this will give us 2 plus 2 minus 3, which will be just 4 minus 3, and it's a 1 by 1 matrix. So that's what we get. And if I have 2, negative 1, 1, and I have 1, negative 2, negative 3, this multiplication is defined because this is a 3 by 1 matrix, while this other one is 1 by 3 matrix. So you expect to get a 3 by 3 matrix. So which will be given by, so row by column. So 2 by 1, and then 2 by minus 2, then 2 by minus 3, minus 1 by 1, minus 1 by 2, by minus 2, minus 1 by minus 3, 1 by 1, 1 by minus 2, 1 by minus 3. And so you get 2 minus 4 minus 6 minus 1, 2, 3, 1 minus 2, and then minus 3. So this is the result for that given matrix. So therefore, let's give a summary of what we have done on the operations of matrices. So summary in form of a theorem. Properties of matrix, addition and addition and scalar multiplication. So one, so if A, B, and C are M by N matrices, and C and D are scalars, the following properties are true. So one, A plus B equals to B plus A is called commutative law. When you change the order, you get the same result. So this is commutative law. Number two, A plus into B plus C is A plus B plus C. This is called associative property or associative law. And number three, C D times A is the same as C into D times A. It's just scalar multiplication. And then 4, 1 times A is equals to just A, this identity multiplication. And then number 5, C into A plus B is CA plus CB. This is called distributive law. And then number 6, if you say C plus D multiplied by A, you get CA plus DA. This is still distributive. Good. And then theorem 2. If A, B, and C are matrices with sizes such that the given matrix operation or product are defined and C is a scalar, then this properties also holds. 1, A into B times C is equals to AB times C. So this is associative property. And then number 2, A into B plus C is given by AB plus AC, distributive. Number 3, A plus B times C is AC plus BC. This is still distributive. And then number 4, C into AB is given by CA times B, which is A times CB. So scalar multiplication. And note that AB is not equals to BA in general. So there are a few cases whereby AB equals to BA. And then number 2, if AB equals to I, where I is identity matrix, then B is the inverse of A and vice versa. So that's what you have. And then note number 3, A times an identity matrix is always A, and an identity matrix times A is always A. So that is to say that A times identity is the same as identity times A. It is just the same as matrix A. So that's what we have. And number 4, if OM by N is a 0 matrix, so 0 matrix are a matrix which has all the elements 0, and A is an M by N matrix, then A plus this matrix, we get A, and B, A plus minus A, we get this zero matrix, and C, A equals to O m by n if C equals to 0 or A equals to 0 matrix. That's all in matrix operations. So next time we meet, we see how we relate matrices to solving systems of linear equations. So thank you.